So here are properties. Just have to make one typo error here. So please make this a plus. Okay, I keep ready to change it in my notes. So those are properties of the cross product. So remember, we talked about yesterday, order matters in the sense that you will get the opposite direction normal vector. So AB is equal to the opposite direction of B cross A. Distributive property works, again, keeping the order. So if A is out front and you're taking the cross product of the sum of two vectors, you can take the cross product of each of them, but with A being the first one. You would switch them around, then you would switch the signs around. Cross product of a vector with itself is a zero vector. Okay, think about the definition of the magnitude of it. You've got magnitude of A, in this case, magnitude of A, sine of the angle in between them. Well, if they're parallel, they're the same vector, right? The same direction. So the angle between them is 0, and the sine of 0 is 0. So, and then because there's no magnitude here, then it is a zero vector, okay, as opposed to just 0. This is what we're going to look at these today. So A, B, and C are coplanar. So coplanar means they are all on the same plane. That means if you take the cross product of two of them, okay, so here's, so I have two vectors there, B and C, okay. If I take the cross product, it would be this. Now, this dot product with another vector on the plane is going to be 0, because the dot product of perpendicular vectors is 0. And any other vector on the plane is perpendicular to this. Okay, so that's this property here. And so it goes from that, if you do not get 0, then that means all of these do not lie on the same plane. Could be that one or all of them. Yep.
So for this one, it doesn't really matter if B dot A times C or C dot A times.
Yeah, it doesn't matter. Okay, any two vectors can be on the same plane, right? But any three can't. So those are just some properties that are helpful. Okay, so question 5 here says show that those three vectors are coplanar. So yeah, doesn't matter which order. I'm going to just do the order that we just did. So first of all, I'm going to, so basically A dot B cross C. What is it going to be? Okay, we want to see, we're not going to say that it's equal to 0 yet, we want to show that it's equal to 0. Okay, so you want to do your B cross C on the side. You can do it in there as well, but if you want to show lines to help you. So, negative 15 minus 3 is negative 18. Minus 24, change the sign. So 30 minus 24 is 6, change the sign is negative 6. And 2 minus negative 8 is going to be 10. Okay, you could, if you wanted to, you could reduce that. Remember, that's a normal vector, okay? So it's really the direction that matters. If you want to divide everything by 2, you could.
I'm just going to put it in there because it doesn't really matter. Okay, and example 6, notice how I have 2 example 5s. We finished that 5 yesterday and now we need 5 here. Anyway, just need to ordering. So this example 6, this is where the cross product is really helpful in coming up with an equation, Cartesian equation of a plane. So you've got 3 points on a plane. To get the vector equation, you need a point and 2 direction vectors, okay? To get the Cartesian equation, you can take those 2 direction vectors and find the normal, and then that's the coefficients of your x, y, and z, and then you have to find that constant term. Okay, so we might want to think about what that looks like. We have A, B, C. A, B, and AC. Doesn't matter, you don't have to do those, you can do BC and BA or whatever. But remember, this as a vector is from the origin up to that point. So that is not a direction vector, that's a point. So AB, if I find AB, then it's from here to here as vectors, because really that's going from the origin. So 2 minus 1 is 1, negative 1 minus 2 is negative 3, negative 4 minus 1 is negative 5. And find AC. For these, I don't reduce any of them. I keep them, just in case, depends on how you come up with that constant term at the end. So I'll show you in a sec. So I'm not going to reduce that to 0, 1, 1 right now, just to make sure that you, if you do it from the definition, that you don't sort of mess up that constant term. So this is going to be 6 minus 10. This is going to be negative 2, change the sign. Negative 2. Okay, so from here, you can use that definition. Oh, gosh. Here. R dot n equals position vector dot n. Okay, so x, y, z dot -4 to -2. Position vector, you choose one of those points as a vector. I'm going to choose A. A is 1, 2, 1. Okay, so that's from the definition of the Cartesian equation from the normal. Question? You always want standard form like that to have the x term being positive and no common factors. Just like for equations of y back in that. Not position vector. You can reduce the direction vector, but you don't have to. Now here, because that normal, remember this is the normal vector coming out of your paper, we can reduce that, but just be careful when you reduce that, okay? So if you do reduce that, then this is the same. If I factor out, say, -2 to get the x being positive, then I have 2, -1, 1, right there. And so you could go straight to your Cartesian equation, right, with those coefficients. So 2x minus y plus z equals some constant term. And you can just substitute a point in it, right? You have 3 points. So if I put in 1, 2, 1 for x, y, z, that's going to give me my constant term of 1, right? 2 minus 2 is 0 plus 1. So then I can just substitute that back in. Okay, so whichever way you want. You can use this, or you can substitute a pointer. You can substitute, even if you don't reduce this, you can substitute, put this in as your coefficient, find the d value, and then reduce it at the end. But yeah, just make sure that your coefficients here, usually we call them A, B, C. Actually, and the constant should be B, should be set of integers. You guys got Z. And then so then A is greater than 0. So take a look at the next one. I'm saving that.
Oh,
Yeah, you don't have to save that. I'm saving that. That's the form that you want, right? Okay, example 7. I added this in here so you can kind of see it a little bit better. So we're finding the equation of the lines of intersection using the cross product. Really, the cross product doesn't, in this case, save a whole lot of time in coming up with the equation of this line. But you might be able to, you might have a partial question like this. Like, what is the direction vector of the line of intersection? And that's where using the cross product is helpful. So it says, find the vector equation of the line of intersection of these using the cross product. So what, if you think about it, we've got two Cartesian equations. So we have our two normals. And we talked a little bit, we used this diagram before actually, so I just copied it out. But the cross product of those two normals is going to be parallel to this line of intersection. Okay, so it's going to, it's kind of hard to visualize. This is a little bit better, but it's going to be coming out of those two at the same direction as this line of intersection. So using the cross product of the normals gives you that direction vector right away. Okay, so that's what you can do to start. I'm going to call this just N1, the normal for the first point, and this will be the second point. So that's going to be 1, -1, 2, and 3, 2, 1. Okay, so the direction vector is going to be the cross product. Again, if you switch the order, if you do it in a different order than me, then it's just going to be the opposite sign. And again, that's fine for a direction vector of a line, right? And really, when it says find the vector equation, there's more than one vector equation, right? You could use a direction vector of -5, 5, 5. You can use it, reduce it, be -1, 1, 1. You could have opposite signs. So 1, -1, -1, right? So there's more than one vector equation. But what, so that's sort of when I mark things, I look for the direction vector to start, right? If yours is not parallel to mine, then something went wrong. And then I check, okay, does your point lie on the line? Like if the direction vector is good, then, and your point on the line is different from mine, then I just check to make sure your point is on my equation, right? Because there's more than one possible. So unfortunately, we're not done this, because this is just the direction vector. So that's why using the cross product, it's not really going to save you a whole lot of time, because you still have to find a point on that line that's common to both planes. So this would be a question where I'd probably say use the cross product to just find the direction vector of your line of intersection. But we're going to do the whole thing just because it's good practice, right? So to get the actual line of intersection, we want to solve this system, and you can use your calculator, right? So you can set up this system. 1, -1, 2, 5, 3, 2, 1, 5, and solve that. Two by 4, I'm just going to copy over one that I have in there. So that's y minus z is -2. So I'm going to let z equal t. So then y would be -2 plus 2. And then x would equal 3 minus 2. So really, that's going to be your equation of your line. So let's compare it to the direction vector that we got using the cross product. So position vector 3, -2, 0. Direction vector -1, 1, 1. Okay, and compare that to the cross product. That's the same. So here, if we factor out 5, we get -1, 1, 1. Hello? But would that point be on the line? Yeah, so you might have it, but it might not be. That's the problem. Yeah. So you want a point that is on both planes. So by just choosing a random, you might not get it.
No, textbook doesn't, like, you have to separate and you set C equals 0 or you have two systems with 2 unknowns and you solve for all of them. The textbook doesn't like that. And then that's
So you choose z equals 0 and then solve for the system? In both, right? So you're saying you're looking for when z is 0 in both planes?
Yeah. And then you have that's how you do it.
Okay. Still have to solve the system though, right? Then it's just two equations into a node?
It's a lot simpler than
Right. Yeah, I guess you could, but choosing one, like you can't choose the whole point. To me, I think about it more in my head, a little bit more, just the whole thing. Just kind of the way I think about it, doing that system. Okay, but the point is that we're finding, we can find the direction vector of the line using the cross product right away. Okay, you don't need to do anything with intersections to know the direction vector of that line. It's the same as that. Alright, so next one, think about that one, determine the Cartesian equation of a plane containing a point. So now you know a point and a line. You need to know, in order to get the Cartesian equation, you need to either know 3 points, so you can get 2 direction vectors, and then use the normal,
Or if you know a point and a separate line, you already know one direction vector and you can come up with another one. Okay? So that's really what you have given to you. I kind of tend to convert this to the vector equation right away rather than the Cartesian equation of a line. So my point here, 1, -2, 1, and my direction vector, 3, 5, and 1. This is like over 1, right? So that means you have a point here, let's say, that's your P. So P is 2, 1, 4. This point Q could be 1, -2, 1. And then you've got your direction vector of 3, 5, 1. Okay, so find another direction vector on the plane. So for example, PP. Okay, then find the normal between D and PP. We get the Cartesian equation. Okay, so if you see that there's a common factor, factor it out, make the first component positive, and then you know that your equation is going to look like that with a constant term, right? And so again, choose your point on the plane, substitute it in, so use
2, 1, 4. Okay, so 6 minus 2 is 4, plus 4 is 8. So D equals 8. And then put it back in your equation. Or you can use the R dot N equals Q dot N. Do the same, and this makes sure it's reduced. Okay, to take a look at the next example, we've already done a question like this using dot product. We're going to see how it relates to the cross product. Okay, so it's actually the same point and same line from example 8, but now we're finding the closest distance. We can do the same kind of diagram again if you want. Okay, so it's exactly the same diagram as the last one. So here we have, we want to find this side here. Okay, we have the direction vector of our line. We have 2 points that join up to be a direction vector on the plane as well. What we do know, let's say we took the direction vector that's in the opposite direction, if we think about it that way. Then, let me just see here. Okay, I'm going to just cut that. So then here, you think about it like this, then this is the angle between them. We're just going to take that acute angle in our diagram. Okay? And so if we think of trig, right, we're wanting to know what this is. So sine of theta is opposite, so the magnitude of Pn over the hypotenuse, which in this case is the magnitude of Vp. Right? And we want to know what Pn is. But we don't want to have to calculate what that angle is. What we have learned is cross product, magnitude of cross product.
So if we have, this is part of the magnitude of the cross product of 2p and another vector, right? Well, we know the direction vector. So think about, I'm just going to do it over here. So the cross product of p, I'll do it over here, 2p. Cross product with the direction vector. There's the magnitude of 2p, direction vector, and then space. So I'm just going to move this over on. Right, that's the geometric definition, the magnitude of the cross product. Okay. So if we solve for 2p sine theta, we divide by d. And then we got these equal to each other, right? So that must mean that these are equal to each other. So 2p we did in the last question. Take a look above. 2p was 133. Direction vector of that line, 351. The magnitude of the direction vector is 135. Okay, we already did this as well back in the last one to get the normal, right? So this is going to be negative 12, negative 8, 4. Oh, sorry, what was it? That's fine, sorry. So it would be, we did it d cross 2p, so it would be the opposite sign of that. So negative 12, 8, negative 4. That's what I just said. Obviously, when you take the magnitude, it's not going to change it. And then reduce it if you can. And wrap it.
say whether this is exact value or not.
Yeah, I'll make sure it does. Usually they'll use that.
Okay.
Okay, and then the last part is just to summarize the meanings of dot product, or scalar product, cross product, or vector product. Okay, so just remember we talked about this when we talked about the scalar product or dot product. This value represents the product of the amount of vector A that is in the same direction as B and the length of B. So it's a product, it's a multiplication. So we talked about how we call it a vector projection. Okay, so if we call this vector A and this vector B, then the projection of A onto B is this, right? So this is vector A projected onto B. And this would be the angle between those two. So if we think about just going back to trig in a right angle triangle, cosine theta is going to be the adjacent side, which is the magnitude of A projected on B, divided by the magnitude of A. So we find this because the dot product is the product of the amount of A, so the magnitude of A that's in the direction of B. So we want to solve for the projection of A onto B. Just by rearranging that. Right, so this is that definition from up here in words, and then we just substitute in for the projection magnitude of A equals theta based on our diagram. So this is really what the definition is, but we don't want to always have to be finding the projection, right? So we know two vectors and the angle between it, then we can calculate. Or if we want to use this to find the angle between it, we can, and we keep it to just those vectors A and B. Okay, so the magnitude in the direction of B, cross product is perpendicular, the magnitude perpendicular to B. Okay, so this value here, and this is the absolute value. Remember, this is a number. That's a number 2, the dot product. So it represents the product of the amount of vector A that's in the perpendicular direction to B and the length of vector B. So it's the same kind of diagram. I'm going to use I'll minimize this a little bit. Okay, so again, same diagram. This is B, this is A, this will be theta. But this vector here, doesn't matter which direction it's going, but this is going to be the projection of A onto the perpendicular to B, right? So I'm going to call this N for normal, I guess you could say. So if we think about sine of theta, that's the magnitude of this side over the hypotenuse. And solve for that. So for that perpendicular. So then by the definition here, cross product of A plus B. So that's the definition. So the magnitude of the cross product is equal to the amount of A in the normal direction, perpendicular direction to B, multiplied by the magnitude of B. So that's this part here. And now we can substitute in. So that's going to be A, B, and here. So based on that definition, take a look in example 11. Which of those, which pair of vectors have the greatest dot product? So dot product is the projection, basically the projection of a vector onto the other, multiplied by the magnitude of the other. Wait for a sec. So you try to just take a look and think about which ones, one of them's got a dot product that's greater, one of them's got a magnitude of the cross product that's greater. Okay, so these, just assume these are the same length. You could get a ruler out. Hopefully I made them the same length. Okay, pretty much did. So then if we do our little triangle here, which is that's not a great triangle, but for dot product, it would be this magnitude times this. Here, it would be this magnitude times by the same magnitude of that bottom vector is the same length. So obviously this one is bigger value, right? That magnitude times this is bigger than this magnitude times the same. So these are the same. So this would have a greater dot product. Okay. And then this one, take a look. That distance there, perpendicular, is bigger than this. So this would be have the greater cross product. Yep.
For that dot product would be based on close to the vector that you're in order for
Yeah, that's true. Yeah, as long as you have that same bottom vector, right? Mhm. Because you're approaching a point sub 1, right? So. And then here, what is the dot product? So these aren't labeled. Well, I'll give you, it is 90 degrees. It should really be labeled there. Okay. So dot product of any perpendicular, so dot product is 0, right? Perpendicular vectors. And this should actually be magnitude of the cross product. So the magnitude of the cross product of two perpendicular vectors is entirely this magnitude times this, right? If you think about the formula, sine of 90 degrees is 1. So the cross magnitude of cross product will be the magnitude of each. Why don't we label these? So then if we label this U and this P, then if the vectors are parallel to each other, okay, then the angle between them is 0. So the dot product will just be the product of the magnitudes. You can see it. That value times this value. So this is all in the direction of V. And then the cross product here, sine of 0 is 0. There is no vertical direction from that. So 0 times magnitude of V is 0.